notes for lesson 3. So the gold leaf electroscope to begin with. Okay, so remember what we had. Okay, we have a metal cap and we've gold leaves. The part that people get caught on here is that that's all the one conductor. Okay, you have an insulation here which is very important. And that insulates that conductor, the metal cap gold leaves conductor, from the metal case. And it is a metal case, and that metal case is earthed. That's a symbol for earth. Okay. Right, and you have a glass front, so you can see in. Right. So when metal cap is charged, the leaves become charged and they are repelled from each other to diverge. The divergence leaves to measure the potential just between the leaves and the case. That should be the case. Okay, and it's useless. So that's it, right? And we use it later on with the proof plane. Okay. Now the Van de Graaff generator, we don't go into detail on the Van de Graaff generator, but remember effectively, okay, we have a dome where there is that build-up of charge. Okay, we have a belt on pulleys. Okay, we have a comb down here, and electrons or charges are sprayed onto the belt there, and we have a comb here where they are removed and they go onto the charge. So it's basically like an escalator for electrons. Okay, the electrons are brought in using the point discharge at comb A, and they're removed using point discharge at comb B. All we're effectively interested in here is that we can get a large charge on the dome. Okay, so then we had a few experiments. So total retard charge resides on the outside of a conductor. So what you're always going to do when you're drawing this is you just draw. You don't have to draw the whole Van de Graaff, but you always say charge. I'm going to do it once. Charge dome of Van de Graaff. Okay, generator. Okay. In this case, we have a can on top. I want to show the charge resides. So that's a metal can. Michael Faraday, who we'll come across later, came up with this, and this was called Faraday's pail experiment. A pail. Jack and Jill went up a hill to fetch a pail of water. A pail was a metal bucket. Okay, so a metal can, right? So that's what a pail is, right? So a charge dome of Van de Graaff generator, a metal can on the top. Okay, and we want to check if there's charge inside. Now the charge is all on the outside of this, there's none on the inside. So what we do is we use our proof plane. So remember our proof plane. This is our symbol for our proof plane. Okay, so it's just a metal base with a insulated handle, and we have our gold leaf electroscope. And remember, all that happens is, okay, I'm going to label this once. I won't label these later, but obviously you label them anytime you're doing them in an exam. Okay, so what we do is we bring the proof plane close to the outside of the charged metal can, bring the proof plane close to the cap of the gold leaves, and the leaves diverge, indicating there's charge. We earth the proof plane to take the charge off it. We put the proof plane inside in the metal can. We bring it over here and we find there is no charge. So charge resides on the outside of the conductor. Okay. Charge accumulates at points. So we have the same setup. Okay, so I'm not labeling anything, but you would label it. And up here we have what we call a pear-shaped conductor, because it's shaped like a pear. Okay, we do the same stuff. I'm going to draw the proof plane. I'm going to draw the gold leaf electroscope. You do the same experiment, and in this case, we find that there is more charge at the pointed end when we use the proof plane to transfer charge than on the curved end. Point to discharge. Lovely experiment. Same experiment again. This time you have, instead of just being pear-shaped like this, it has a real point. Okay, remember, point discharge, but we'll explain it here in a second. But what happens is there is a stream of ions that go away from the point. And to check that, we see what's called an electric wind. So we put a candle here. Okay, so when we charge the Van de Graaff dome, we see the candle blowing away in the wind. Okay, why? Okay, well, we'll draw example here, and this is something you could be asked. Okay, so we have the point, and there is a very high charge density, which means a huge amount of charge in a small area. That very high charge density ionizes the gas around it, or the air, okay, into minus and plus ions. Okay, you have to say that. Okay. Okay, no, it's actually missing from the notes there, so we're going to put it in. Okay, so there's a large electric field around the point, and air is ionized. Okay, the negative ions from the air are attracted to the point and neutralize it. So the negative ions go to the point, and they neutralize it, so there can't be a build-up of charge if you have pointed bits on the top of the Van de Graaff generator, and the plus charges are repelled, and you get the wind, which blew the candle. And effectively what's happening, even though they're different charges, is the plus charges are leaving the point and they're being repelled into the air. Okay, so you're losing charge through the points. That's why Van de Graaff generators work better if they're shiny. If they're not shiny, if they're rough, there's loads of little points, and this is happening for them, so you can't build up the same charge. Okay, so that was our interesting lesson on the Van de Graaff generator. So that you have them all there on one page. Very important to be able to work your way down through there. They're very similar experiments. Thank you.